Alright, in this video we're going to talk about more applications of graph reductions and graph modification algorithms. So in this first problem, which is a very real-world problem, is you just discovered your best friend from elementary school on Facebook, and you both want to meet as soon as possible, but you live in two different cities that are very far apart. So to minimize your total travel time, you agree to meet in an intermediate city, and you both immediately start driving to that city. But the question is, what city should you choose to be your intermediate city to minimize your total time? So in this problem, you're given a graph, which is modeling the cities and roads between the cities, and each edge has a weight, which is the time required to travel between those two cities. So very standard example, it's basically a Google Maps turned into a graph. Now in this problem, you start at vertex P and your friend starts at vertex Q, and you want to find the intermediate node T that allows you and your friend to meet as soon as possible, assuming you leave immediately. So there's no delay in your leaving times. So if we draw this, we have our graph G here, and we have P and Q, and then we have, say, some possible T. So the question is, how much time, at what time exactly will you two meet at T? Well, in particular, so you're closer to T, so it's going to take you some amount of time, and so maybe you're waiting there at T while your friend's still traveling. So overall, it's going to be the time you actually meet will be the max of the times you both take. And the time friend takes. So the max of those two is the actual time you're both at T at the same time. Before that, only one of you might be there, but you have to wait for you to both get there. Okay, so then what's the best possible options here? What's the best possible time you can take? Well, that's just going to be the shortest path from P to T. So the shortest path from P to T. And then what's the absolute fastest your friend can get to T? Well, that's just the shortest path from Q to T. So assuming you have those both computed for all T's, then the optimal solution, the best T, we're just going to try them all. So it's just the minimum of all T of the maximum of distance from P to T and distance from Q to T. So here it's a little weird because it's a min-max. So really you're solving a minimization problem. You want to meet as soon as possible. It just happens that this max comes into the problem because of how time physically works. You have to wait for the latest of you two to get there for you two to meet. So although there's a max in the problem, the goal of the problem isn't to maximize anything. That just happens to be there. So you're minimizing this, and both of these things are also minimal values. They're the shortest paths. Okay, so that's the best T. We'll just loop over all possible T, compute these shortest paths, and take the max, and then we take the min over all of these possible maxes. And how are we going to compute these? Well, the most efficient way to do this is to pre-compute them. So we can run Dijkstra 2 times, one starting at P, so that we have the shortest path from P to any other node T, and then one starting at Q. And we'll just compute both of these in advance and then compute this min. And then overall, this is going to be E log V, because we run Dijkstra twice, so that gets absorbed into the big O. We don't care about constants. And then to do the minimum, well, this minimum is over all possible intermediate nodes, so that's just O of V time to do. And to be precise, it'll be something like O of V plus E, but either way, it'll get dominated by the O of E log V. So that's our total running time. The whole pseudocode's right here. It's very simple. We just pre-compute the distances, the two distance functions for P and Q respectively. And this gives us this overall distance function. That's the d of P to V, d of Q to V. And then we just do a simple loop every time we find a better estimate. So if the current vertex T, if it's max of both, which it's total wait time, so this is the same as the total wait time. If that's better than our current total wait time, which is stored in time, then we just update it and we just loop through and continue. So clearly the running time is dominated by these two calls, and so it's O of E log V.